Previously, we saw how to relate voltages to electric fields. And I'd like to finish up this bit of treatment of electric potential by taking a look at an application called a capacitor. So what a capacitor is schematically is it's a pair of plates. Here I'm just imagining a couple of metal plates. And the spacing between the plates is small compared to the dimensions of the plates. We'll say this separation is D. We'll say the area of the plates is A. And then somehow we, usually by hooking up a battery or something like that, we move charges around such that one of the plates will hold a charge plus Q. The other plate will hold a charge minus Q. And breezily, we usually say that the capacitor stores a charge Q. Really, the total charge stored in the entire device is 0. But what we've done is we've separated charge. We've put plus Q on one plate, minus Q on the other plate. Now, nothing says that it has to be metal plates, and the way I have it drawn, I'm showing two flat plates really close to each other. Many other arrangements are possible. For instance, in a computer memory, the capacitors that are used to store the ones and zeros are just traces on a semiconductor. And even some other things that you might not think of as being capacitors kind of are. For instance, an electrical synaptic junction is another example of this. In a normal electric circuit, we charge this up by moving electrons around. In an electrical synaptic junction, you charge it up by moving around calcium and sodium ions. But electrically, it's still the same thing. You've got a couple of flat surface, couple of surfaces closely spaced to each other, holding opposite amounts of charge. Okay, now a typical capacitor that you would see on a printed circuit board or something like that, usually, unless it's a really low value capacitor, one that's designed not to hold a whole heck of a lot of charge, most of them are actually more of a cylindrical shape, but that doesn't really affect our discussion here. So I'm going to kind of just draw more of an edge-on view just to think about it a little easier. So if I'm holding charge plus Q here, minus Q here, we've already seen before that inside the capacitor, the electric field, which will be running from positive to negative here, this will be nearly uniform. Inside the capacitor. By that I mean pretty much no matter where I am inside the capacitor, except for maybe right at the very edges, the electric field strength and direction is pretty much always going to be the same. And in a bit, I will mention that I won't draw it in now. We'll worry about it later. But also, just for completeness sake, there will be a tiny bit of electric field outside the capacitor. That's not relevant to what we're talking about at this exact moment. But the point here is that we have an electric field and we have a separation. So if we have both of those, what that means is that across the plates, I have to have a voltage difference. And since this is basically a uniform field, that would be the magnitude that would be equal to the electric field strength times the plate separation. Now, usually when we try to describe these things, what we're more interested in is you're going to hook this up to a battery. Batteries are rated by their terminal voltage. So you're going to say, okay, I'm going to apply a battery of so many volts across this thing. How much charge can I store? And To that end, we will say that the charge stored on the plates, which remember just means plus Q minus Q, we've just really moved it around, will be equal to C delta V, where C is a quantity called the capacitance of the device. So our units of capacitance are the farad. This is named after Michael Faraday. Long story why the AY got dropped off the end of his name in the unit. But anyway, a farad is a coulomb per volt. And it turns out that the way that SI units work, a farad is actually a pretty big capacitance. It's not to say that you can't have a 1 farad capacitor. You totally can. And actually, you'll see like on a lot of computer power supply boards and stuff like that, in order to prevent the computer from rebooting if, say, the dryer kicks on in the house and you have a momentary fluctuation of current throughout the house. In order to keep the computer from rebooting when that happens, they'll usually stick something like a half farad capacitor on there. But it's a half farad capacitor, but it's only designed to operate at fairly low voltages. But even so, we're talking about a device that's maybe about a couple centimeters in diameter, maybe half a centimeter tall, something like that. Pretty big device. If you're working at even a little higher voltages, like say 12 volts for an automotive system or something like that, people do use 1 farad capacitors in audio systems for cars. Basically, if you've ever known somebody who's put ridiculously big subwoofers in their car, in order to balance out some of the magnetic considerations of the speaker that could limit its performance, typically you wind up wiring a capacitor into the circuit. This is something we'll get into later. You try to get it operating closer to what's called resonance. But anyway, it turns out that if you've got ridiculously big subwoofers that are pretty much taking up the trunk of the car, you're going to need a capacitance on the order of about a farad. And then it turns out that those capacitors are usually about the size of a coffee can. So 1 farad is an amount of capacitance that exists, but devices don't usually get much bigger than that. And most typical devices, just to give you some sense of intuition, like the sort that you would put onto a printed circuit board or something like that, they will range in about the 1 picofarad to maybe about a microfarad or so. Okay. And what's going to dictate the capacitance, like I said, it is the ratio of the charge held to the voltage applied. But the higher the voltage applied, the stronger the electric field. If I have a bigger plate, I will have more points for my electric field lines to start from, and we always start and end on charges. So if I have a bigger plate, the capacitance will be bigger, and by the same reasoning, my battery voltage isn't going to change. If I make the spacing between the plates smaller, that would increase the electric field strength, which would again mean more electric field lines, meaning more charges that the lines would have to start and stop at. So the bigger the plates and the smaller the separation, the bigger the capacitance. For this kind of parallel plate capacitor design, an analysis beyond the scope of this treatment will give you that the capacitance is equal to epsilon naught A over D, where A is the area of the plates and D is the separation of the plates. Epsilon naught, just as a quick reminder, is our friend the electric permittivity of free space, which is basically just a name. It is 8.854 times 10 to the negative 12 coulombs squared per Newton meter squared. And you should be able to convince yourself that a coulomb squared per Newton meter squared is a farad per meter. So you can also write it that way if you prefer. And our friend epsilon naught did make an appearance before. That was in Coulomb's law. We buried it by writing K, but that K is 1 over 4 pi epsilon naught. So we've run across that before. Now, if the shape of the plates is not just a couple of flat plates, like I mentioned before, a lot of devices are actually cylinders. You wind up getting a little different relationships, but the main idea is still the same. The bigger the plates or the smaller the separation, the more charge you can hold. Okay. Now, it turns out that a lot of times what you want to do is hold more charge in these devices for the same area. And a way that you can kind of do that is to insert a material called dielectric, which is just a piece of insulating material. So to give some sense of this, let's say, and again, I'm just looking down from above, I've got capacitor plus Q minus Q. I'm currently disconnected from the battery. So in other words, there'll be no way to change the amount of charge on the plates. Now what I'm going to do is I'm going to bring a piece of paper, thin little piece of paper right nearby, like so. And I'm going to go ahead and insert that piece of paper into the dielectric, into the capacitor like so. So what I'm going to ask you as a pause the video moment here is what happens to the electric potential energy of the system. So pause the video and get back with me. Okay, so what turns out happens is that the electric potential energy decreases when I insert the dielectric. And probably the most straightforward way to argue that is that we've seen before, if I hold a charge near a piece of paper, for instance, you would induce a polarization in the paper that attracted the paper. So in other words, the paper bit wants to fly into here. So if you were to somehow do it super artfully, that you release it just the right place so it'd end up just stuck between the two plates like so, it would literally fly into the plate. Its kinetic energy would increase. And since its kinetic energy is increasing, that energy had to come from somewhere, and that somewhere turns out to be the electric potential energy. Now we can argue this maybe a little differently. So again, here I'm just going to draw. Here's my plate plus Q. There's my plate minus Q, like so. And here I'm just going to insert my piece of dielectric material, paper, whatever. Now, what's going to happen here? This plate is positively charged. This plate is negatively charged, right? So we're going to end up, all of the molecules are going to wind up inducing a bit of polarization, like so. I'll draw just a couple more. So all these molecules that make up the dielectric, be it a piece of paper, whatever, they all wind up inducing a polarization. That's what allowed it to get sucked into the plates in the first place. But now what that means, there's a couple ways you can think about it. One way you can think about it is that we've had this electric field already. And now what you can start to say is, oh, but if I am having to stop at negative things and start at positive things like this, one intuitive way you can think of it is to basically say that since the electric field line ends here and starts here, this is actually decreasing the density of electric field lines everywhere. Anywhere you've got a molecule, we've broken the electric field line and inserted the molecule. This actually decreases the density of electric field lines. Or the usual way that it's more described is you just say all of these dipole moments wind up inducing an electric field in the dielectric that points the opposite direction of the electric field you had before. So what this means is that my new electric field in the dielectric is less than what it was before I inserted the dielectric. And it's less by a factor kappa. So that is a lowercase Greek kappa. So just as a quick reminder here, using that special paper that we all used in second grade, it's a little half height K. This little hooky right here isn't necessarily required. I use it because if I don't, my half height Ks tend to turn into full height Ks, and I can't tell my kappas apart from my Ks. But anyway, this is a number that gets called the dielectric constant of the material. ELECTRIC, constant. And it doesn't have any units. It's just a number. Typically, and it's going to be a number bigger than 1. And basically, it turns out that for pretty much any electrical relationship you have, if instead of it being in a vacuum like we've been analyzing, you can pretty much just everywhere you ever saw an epsilon naught or something that had an epsilon naught buried in it, you can replace the epsilon naught by kappa epsilon naught. So if there's a dielectric present for our parallel plate capacitor, it would now become kappa epsilon naught A over D. Now, if this is air, this kappa is no big deal. It's a number just barely bigger than 1, and so you can generally treat it as 1. But in practice, when people are designing capacitors, they intentionally insert dielectrics because this winds up allowing you to store more charge. The whole point is if I do hook a battery up to this, it is going to move charges until the voltage across the plates is the same. If the dielectric has the effect of weakening the electric field, you're going to have to move even more charge in order to get the electric field strength up to what you had before in order to match the battery voltage. So as a result, you can move and store more charge, which is usually desirable in capacitors. For weaker capacitors, sometimes literally paper is actually used as a dielectric material, but there are all kinds of specialized boutique materials that get used for this purpose. All right, so now I've mentioned hooking up a battery to a capacitor before. So let's think about charging a capacitor. So again, schematically here are my two plates. Let's imagine I hook a battery up across this. I'm feeling particularly cheeky, so I'll make it a car battery. There. So let's say this is the positive terminal of the battery. That's the negative terminal of the battery. Now, what's going to happen here is while charging, and we'll get into how this works in a bit, but just for now, we'll just say while charging, let's use a different color. While charging, what the battery is going to do is it'll move electrons around the circuit like this. So as it pulls electrons off of this plate, that will leave behind positive charges. So that's how this plate will pick up its charge plus Q. Meanwhile, the electrons will get deposited onto this plate, so that will become a negative. So they'll pick up our charge negative Q, because however many came off of this plate will end up over at that plate. As we'll see, all batteries do is just move charge. Remember the Van de Graaff generator with the conveyor belt. Whatever goes on the conveyor belt has to come back off the conveyor belt on the other side. So the thing is that the battery can't just move the charges for free. And the reason for this is what I was mentioning before. While primarily the electric field that we get is between the plates, it turns out that there is a weak electric field outside the plates. And I'll just draw it in a few lines to indicate that. This region right here, this gets known as the fringe field. It's a lot weaker than the field in the interior, but the point is it's not zero. And so initially, when our capacitor is fully discharged, it turns out the battery really can move the first electron for free. There's nothing for it to work against. However, as soon as it moves the first electron, this plate will have picked up a positive charge, this plate will have picked up a negative charge, and this means that right here at where the wire junction is to the capacitor, we now have a little bit of fringe field. Let me fix that there. As we're pulling the electrons off, the electric field is pointing to the left. But since the electron is negatively charged, it'll be feeling an electric force to the right. This means that the battery will actually have to do work to pull the charge off the plate because it wants to come back onto the plate. And by the same token, actually it'll have to do work to shove it onto this plate. We're building up more and more negative charge. We're trying to shove more electrons onto the plate. So we're moving charges from where they electrically want to be to where they electrically don't want to be. So anyway, the strength of the field that you have to work against is proportional to the charge held. And so while charging here, since we aren't changing the spacing between the plates, the voltage across the plates is also the same. If I plot the voltage as a function of charge, and I get to my final charge Q, I'm at my final voltage, delta V there. We can figure out how much energy got stored in the capacitor. So it turns out that the work that we had to do to move all the charges will be 1/2 Q delta V. And why is it going to be 1/2? Well, it's going to be 1/2 because one way you can think about it is just to say initially I moved the first electron through a 0 volt difference, the last one through delta V. So the average electron went through V over 2. And if you're fine with that, that's fine. If you want to be more fussy about it, then what you wind up doing is saying, well, if I think about moving a small amount of charge, we'll call it little q like this. So we'll say that was some small amount of charge, little q. The work I would have had to do to move that would have been little q times whatever the voltage is as a function of the charge on there. So this area right here would be the work that had to be done to move a small amount of charge, little q. And the idea is I could play that same game here. I could have played that same game here. And so the total work done to move the charge, all the charges, will be this area under the curve right here, which is the area of a triangle. And so you can also say it that way, that the energy stored will be 1/2 Q delta V. By definition of capacitance, you can rewrite this as 1/2 Q squared over C and 1/2 C delta V squared. And I find all of these expressions to be roughly equally useful. One thing that I will introduce, not mostly because I don't know where else to put it, is the energy density. So this gets written as lowercase u. This will be equal to the energy stored in the capacitor over its volume. We did similar stuff like this with fluids, where we had talked about kinetic energy density was the kinetic energy of the fluid divided by the volume of the fluid parcel we followed. Then that just ended up with us replacing the mass. When we saw we'd have a mass of fluid over its volume, we'd replace that with the density. Extending on that idea, we can do the same thing. So this will work out to be 1/2 kappa epsilon naught E squared. I'm not going to derive it, but you're certainly welcome to go and convince yourself of it. Now this result I just did for saying that this is the energy stored in the capacitor, how much work we had to do to move the charges, divided by the volume of the capacitor. And then I wind up arguing that it's proportional to square the electric field. Now it turns out in a much more sophisticated analysis that this is just true in general, even in the middle of space. If there happens to be an electric field, we can associate an energy density with it, and it goes as the square of the electric field. I mostly mentioned this to just kind of put a pin in this thought for when we get to doing electromagnetic waves later, when we're thinking about where light comes from. All right, so just to kind of finish this up, let's just take a look at a quick example here. So let's make a capacitor out of a couple of discs, like so. So we'll say that the diameter of the discs is 2 centimeters, and they are spaced 2 millimeters apart. And we'll say that they are charged and that the electric field strength between the plates is 500,000 volts per meter, which is a typical kind of value. So the questions here are, what is the voltage across the capacitor going to be? And how much charge is stored on our capacitor? All right. Well, as far as getting the voltage, remember inside a capacitor, the electric field is pretty much uniform. So we can say delta V equals ED, our relation for voltage difference given a uniform field. So this will be 500,000 volts per meter. And we'll have to take those millimeters, turn them into meters. So they'll be 0.002 meters to give us a nice round 1,000 volt potential difference, which is a value that can happen in electrical applications. So it is a reasonable thing. Now, as far as the charge held, we would say that Q equals C delta V. And we will put in that this is epsilon naught A over D. Since I didn't specify a dielectric, we'll just assume that the dielectric constant is 1. So this is going to be epsilon. So we can just start plugging it in here. This will be epsilon naught will be 8.854 times 10 to the negative 12 farads per meter. The area is going to be pi times 0.02 meters squared over 4. The separation is going to be 0.002 meters. And we worked out that was a 1,000 volt difference. Punch that through your calculator and you'll get 1.39 times 10 to the negative 12 coulombs. So about 1.4 or 1.39 picocoulombs, which is a reasonable value. You tend not to store ridiculous amounts of charge unless the devices are very large. All right, so that will do it here. Catch you in the next video.